such thing as a gravitational pull.
Okay, let's break it down for you easily. Nice and easy.
Yeah, no, hold on. We won't break it down easily. What direction do gas? Yeah, what direction do gas molecules travel in? Simple, like what direction do gas molecules travel in?
Gas molecules move in all directions.
There you go. Stop right there. Pause. Stop right there.
Rob, you just walked right into it, bro.
Right.
Yeah.
Gas molecules will move in all directions. So it depends on what.
No naturally observed phenomenon of all things going down to the center of mass.
Why are you speaking when I'm...
Because you're just describing how there's no naturally observed phenomenon of things going down to the center of mass at 9 meters per second per second.
Because gas is your only guy? What about a rock?
Let's see, gas. What about smoke?
Hold on. What about a rock? What about a stick? Why does a tree fall? Why do you fall off the tree? Why when you throw a ball up in the air it comes back down? Why are you not concerned about those? Why is your only thing gas? Is everything gas?
The air we breathe is gas.
Is everything gas?
That pushes on the wings of an airplane 40,000 feet above my head is gas.
Guys, calm down. Hey, Robert, please. Hold on, Robert. Hello.
We can hear you.
Hello. Yeah, my bad.
I had the YouTube still playing. I thought everyone was talking over me.
Yeah, dude, I did that for like a solid minute and a half one time. It was the most embarrassing thing of my life.
Wow, thanks. Okay, all right, you guys know the deal. Stop with the yelling and talking over each other. It's that simple. Thanks.
I apologize. Sorry, Robert.
Yeah, no problem. I mean, what I'm saying to you is that you're only stick here.
Hello.
We can hear you.
Hello. Yeah, my bad.
With a container. So we know that a container will stop gas. So we know that will happen. But what is the evidence that gas will go downward without a container? That it won't continue going up?
Right. The pressure gradient in your atmosphere is your demonstration that gas does not continue to go up. Right? It's gradients. There's 14.7 psi at sea level. As you rise, it gets less and less.
Mm-hmm.
That means gas is being held to the ground on a bias. There's something there that's holding it there bias-wise, right?
Yeah, there is something holding it there. But we can make gradients within like a contained system. But
really,
you're saying that there can be a pressure gradient without a container. Can you show this?
Yes, the atmosphere.
Show this, Rob, without using the Earth, please?
But the flat earthers assume there is a container there on the flat
Earth. The atmosphere, you cannot show gradient inside of a box or a glass without introducing an outside factor. So what I'm trying to say to you, on Earth there are many factors. There is air in the Arctic, there is air in the Caribbean. Right? And all of those places maintain that.
What about electrostatic?
You have to manipulate these temperatures inside of your container in order to try your best to mimic naturally.
Robert, please stop screaming. Please stop screaming. Also, Vaxi, if you're still here, you were yelling directly into your microphone, and it was a story. Please don't do that either. Thank you.
Yeah, Robert. What about electrostatics?
It's not electrostatics because it depends on charges. Electrostatics are charges. What charge are you?
Everything has charge, dude. Everything, including gas.
Okay, what is the charge of a rock? What is the charge of the ground?
What do you mean, what is the charge? Something that's denser is going to have more charge.
Let's not negate from the last point, please. Let's try to say one point at a time so we can actually get somewhere. So other than the atmosphere, which is what is in contention, right? We're trying to figure out what's happening in the atmosphere. So we would like a demonstration of how, gas pressure can be contained or have a gradient without a container. That's what the request is to Robert.
Not even a gradient though, because then he's like, oh well, then you can't explain a gradient on a flat Earth.
You can have gradients of gas like within chambers. Like there is examples of that. Like
the main thing is in a vacuum chamber, all of the atmosphere and water on Earth will basically boil away because it's trying to seek equilibrium in a vacuum chamber.
Right. So in a vacuum chamber, it's actually I was looking to see if the gas fell. Because we know gas rises. They say it's because of buoyancy, whatever. But in a vacuum chamber, does the gas fall or rise? I was not able to see that the gas fell due to gravity in a vacuum chamber.
It just disperses. It doesn't fall or rise.
Right, yeah, it's all equally dispersed. You're right. So, what is the evidence that the gas is going to fall or have some sort of gradient or whatever without containment, other than the atmosphere itself, which is what's in contention?
Right. So, again, even in a vacuum, your gas will gradient. Over time, it will gradient naturally.
Can you prove that?
That's funny because now you don't need it. Yeah, that's funny because now you don't need. Hold on. I'm trying to respond. Literally, I've been listening. Now let me respond, please. What the heck is wrong with you?
Hold on, brother.
No,
Dude,
Robert.
I'm trying to respond, Rob. You said something.
Go ahead.
Yeah, even in a vacuum, you just said that the mass of the gas molecules is going to, find equilibrium and create a pressure gradient. So now you don't need a center of gravity for your pressure gradient? How funny is that? Hilarious.
What? That even makes sense. Even in a
Yeah, it does, dude. In a vacuum, gas molecules are going to arrange into a density tower gradient, pressure tower gradient, right? Due to the mass from the gas molecules themselves, rather than them coalescing around a center of gravity like Earth's gravity. So there you go. Your model doesn't even require Earth gravity to form a pressure gradient.
Also, dude, I'm pretty sure you're talking about, like, if it's in a container, it's already reached its equilibrium, so then you'll have a gradient. But if it's in a vacuum chamber on this ball in the center, it's to disperse until it's reached equilibrium, and then it's going to find its gradient. Not before.
How many times you plan on being wrong today? If you're like trying to break a record or something?
Robert, do you have the evidence the gas will fall in a vacuum chamber without buoyancy? That's the thing, because we know it'll rise. You say it's because of buoyancy, but you say it'll fall if there's nothing else present. We just want some proof of that, or I do.
It's actually wicked doublespeak. So they also say that the force of the mass, like the force of the mass from the from the gas molecule, that the thermal motion is actually stronger than the gravity caused by the mass of the gas molecule. So it's doublespeak. They don't know what they're talking about.
No, it's doublespeak. When you even in a container, gas will gradient. Even in a container, gas will gradient. So if you have a container that is, say, 20 feet tall or 100 feet tall, and it's filled with the same amount of gas that's in the atmosphere, right? You don't pressurize it, you don't do anything. You just open the top, you let gas flow in. When you close that cap, the heavier gas molecules will go towards the bottom, all right? Over time.
There's no gas in a vacuum. Sorry, I'm asking.
Hold on, everybody. Over time, heavier gas molecules go towards the bottom.
Robert, please. Vaxi, you're yelling directly into your microphone. It's hard to hear and it's very loud.
Oh, is it? My bad.
Just pull away a little bit, please. Thank you.
Yeah, I got you. Robert, are you saying that if in a vacuum chamber, when we take the air out, the gas will go towards wherever whatever is taking the air out, it will go towards that mechanism. But if you already have a gas chamber and then let in the gas, it will.
If you have a chamber, you just open the top and let gas in. Don't pressurize it. Just let gas flow in there. The heavier gas molecules will go towards the bottom. We
understand that. That's buoyancy. But I would like proof that lighter gases do fall to the ground because gravity's at play. That's what you're saying is holding in the lighter gases. Can you prove that in a vacuum chamber that the lighter gases will go to the bottom?
Lighter gases will fill the entire container. So if your container has just hydrogen, it will fill that container.
But the thing is, it doesn't fill the entire container of space. So
why doesn't it fall?
Can you make it actually analogous?
That's true. Good question.
Well, what's the question?
It doesn't go and disperse into space. You're saying that gravity's holding the gas down. We just would like that demonstrated with no other gases present.
We know what we have.
So we're removing buoyancy, right? We're just trying to see if gravity holds down these lighter gases.
Yeah, because you said gas fills the entire container, and then the lighter gases what rise, and the denser gases go towards the bottom. Right. But that's with a filled container, but space isn't a filled container. So could you demonstrate it with a container that's not full of gas, and where the dense gas goes towards the bottom, the lighter gas stays around the middle, and then there's literally still a vacuum at the top? Can you demonstrate that? Have you demonstrated that?
A vacuum at the top. You understand that vacuums don't stop things, right? You know that, right?
No, dude, a vacuum chamber. You still have nothing, no gas at the top. Have you demonstrated that?
What they actually claim is you would need a mile-high chamber to observe that change in density. Yeah, because if you have just a normal-sized vacuum chamber, no, the thermal motion, that force is going to be more present than the supposed force of gravity.
So it has
so that density tower gradient is only going to be observable with a mile-high vacuum chamber. And I'm sure Rob knows that, but he wasn't going to say it.
Yeah, so it's never been demonstrated with a half-full container. It's only been demonstrated with a container that is filled with gas, where the gas distributes equally. So,
you would remember we're in there's gas around us at all times. So, whenever you put gas inside of a container, gas is going to want to be and you open it, it's going to fill that area around with where there's other gas. That's what it should do. Now, if the reason why gas doesn't flow off into the vacuum of space is because there's an equilibrium that has reached. The hydrogen molecules, which are the lightest gas, and the helium guys, they are just far enough from the Earth's gravitational impact They have reached an equilibrium. There's no more heavy gas to buoyant them out. They are the boss at the very top, and they are now sitting at the top of this entire ocean, and they're now free to be impacted by the Earth's gravitational pull by themselves.
You're confused about what we're even contesting.
What I'm saying to you is that on Earth, when you're on the ground, you're going to have to get away from all this ocean of air in order.
Yeah, so basically you're saying it's never been demonstrated, and you can never prove this.
No, it doesn't need to be. What I'm trying to show you, the behavior of gas when it gradients in your atmosphere, that is the demonstration that low pressure can exist next to high pressure. So
well, yeah, I don't
so you don't need to drag it to 10 to the minus 4. That is going to be the result. As you go higher, by the way, the gas pressure is falling, right? It is falling. So there's going to be a point, obviously, where it gets to that equilibrium, right? Hydrogen and only helium, obviously.
Yeah, so what's your point? I don't dispute that there is a gradient.
Containers do not gradient in that way. There's nothing inherent inside of a container. There's no fingers grabbing molecules and say, you stay there, you guys come up here, and you guys are safe here. You guys say, containers do not do that. You get what I'm saying to you?
I'm not sure. But what we were asking essentially is like, in a vacuum chamber, can the gases still fall? To show that yes, gravity can hold gases down. Without going into space.
Well, it's a vacuum chamber, so it doesn't have. So you have a vacuum.
If you were to introduce helium to a vacuum chamber,
right?
You know what I mean? Would it rise or fall or whatever?
Yeah, no, it's going to fill the container. It's going to go to the bottom of the container, and it's going to be filled with container.
Does it?
Right. Yes.
Dude, does it?
Yeah, it does.
It does, yeah.
It does.
If you only put helium in a vacuum of container and you only pump helium, it's going to go to the bottom as well. 100%.
Well, no. Okay. So if that's the case, what even is the dispute here?
Does gravity act to pull down gases?
Why does the helium go to the bottom of the container?
Wait, we just established it doesn't.
No, helium does indeed go to the bottom of the container. If it's the only gas inside your container, it will go to the bottom 100%.
Helium gas. We're talking about helium gas.
Yeah, there's a bunch of videos where they'll put like a helium balloon inside a vacuum chamber and then suck all the air out, and the helium balloon will fall every time.
That's a balloon, dude.
The balloon will fall.
That balloon filled with the gas will fall.
Because remember, helium balloon outside floats to the.
Wait, Robert, you didn't answer my question. Robert, does the helium gas fall? Because you just double spoke. You said earlier that it would disperse evenly throughout the container. Then just now you said it would fall. So which one is it?
That's what disperse evenly means. That means it's going to.
Disperse evenly is not having any sort of bias towards one region of the container.
We understand that. What I'm saying to you is that the gas is going to go to the bottom as well. That's
what?
Yeah, the helium gas is going to go. No.
First of all, you're contradicting yourself. Second of all, where's the evidence?
Helium, it will go to the bottom of the container as well as to the top. It will fill. Right.
Does it have a downward bias?
Yes, there is a downward bias.
Okay. What are you referencing to state this? Because I think you're just making this up.
Take your barometer test. If you have a very small chamber.
Can you cite your source?
Like what source?
Give me your source for your statement.
Source for taking a barometer test inside of a container?
You said the helium will have a downward bias in a vacuum chamber. You said it will fall. Yeah. Where did you get that?
Okay. Everything goes to the ground.
Okay, so have you done this or not? Are you referencing something that's been demonstrated and done, or are you just saying based on logic you're assuming this will happen?
Yeah, based on logic, because mass attracts mass, right?
Okay, so you have no evidence for your claim, but you're just asserting it as if it's fact, even though you contradicted yourself earlier saying it would disperse evenly.
No, it will disperse throughout the container.
Define disperse.
Over time. Over time, there will be a gradient. I guarantee you this.
How do you know that?
Right? The reason why there's going to be a gradient is because of that gravitational impact.
Okay, that's what we would assume. Now prove that that's what actually happens.
Okay, but again, we're only dealing with gas.
Can you prove it?
We're only dealing with gas here.
Can you prove it? Yes or no?
Are you saying we are not only gas on Earth? We're leaves and trees and rocks.
I'm not saying anything other than asking you to prove your statement.
I'm trying to understand the relevance of only doing an experiment with one element.
There is relevance, and it's because you can take out the buoyancy. Like, we're not dealing with buoyancy, we're just dealing with gravity.
Remember, gas molecules inherently move rapidly. That's why they're gas. So
I just love how he's
focusing. But what I'm trying to get her to understand is that focusing on a material that has that property does not give you an accurate picture of our world.
But in the atmosphere, you're saying it doesn't go in all directions. Like there's something containing it.
Robert, I got a question. In a container with no gravity, what would gas do? If you put gas into the container, what would it do? With no gravity.
Yeah. Without gravity, it. Sorry, I got a call here. Yeah. What happens is it will tend to spread throughout the entire container, even in microgravity.
Okay. Actually, what it should do is coalesce into a cloud, where it's denser in the center.
Well, what I was going to say is that what I was going to say actually is that wherever there is more of the gas, that's where it's going to be.
Yeah, just checking to see if you understand what you're talking about, man.
Well, there's some people looking for the ruler.
Now you just need to prove your claim.
Which claim?
Your claim that the helium gas in a vacuum chamber will go down due to gravity.
Due to gravity, all things go to the ground.
Dude, prove it.
Show that.
I'm not proving. Dude, if you come up with a table, you go to the ground.
Cite something, dude.
Yeah, go ahead and substantiate that.
Hold on, let me say this. You have fast cars, you have slow cars.
Oh my.
You have
Dude,
fast cars, you have
you
slow cars.
already explained to us your logic. Just cite something,
Hold on.
dude.
No,
Cite an experiment.
why? Listen.
Oh my.
You have fast cars, you have slow cars.
Doesn't matter.
Fast cars don't behave like slow cars. They don't. Right?
Doesn't matter.
You put them on a track, fast car is going to do something a little bit different than a slow car. So,
Robert, cite the paper. Robert, cite a paper where that happens.
What I'm saying to you is take into consideration what you're dealing with. You're dealing with gas versus a rock or pebbles or sand.
Yeah, so can you cite something, dude? Just give us an experiment.
Okay, all right, let's cite something. So you want to know if helium
Oh my.
hold on. You want to know if helium hold on. You want to know if helium will gradient in a container, right? That's what you want to know, right?
We want to know if helium will go to the bottom of the of the vacuum chamber, dude.
Okay, all right. That's one thing you want to know, right?
Yeah.
Okay.
And cite a scientific paper that backs it. Don't just say, oh, yeah, it does. Trust me, because I think you're a spinning ball.
Well, it's not a spinning ball. That's the first problem there.
Yes, it is. Okay, well, all right, fine. It's a stationary ball then. Okay.
It's not that either.
That's not the point.
Ball,
Stop. Yeah, that's all you can do, Robert. You just like to pick on semantics to buy time for yourself so you can think.
There's also, I don't know where you guys get the spinning ball now.
Yeah, you're so dishonest, dude. You know what he means. Come on.
Give me the scientific paper. Come on. Yeah, I should probably click that so I can say Robert's like, Earth's not a spinning ball. I'm like, okay, great. Thanks for playing.
Yeah, you're welcome. All right, here we go.
Here we go, nothing, dude. You've just been like presenting all these wrong arguments.
Robert is a great benefit to the flat Earth. I mean, I actually kind of appreciate him for helping
I
convert
agree.
people.
I
You know?
agree.
Makes the job easy.
Exactly. He makes his side look bad. Even if he's right, he makes his side look so bad.
How? You guys
Yeah, I show it to Glover for my friends.
Well,
Yeah,
Robert,
You misrepresent your
very poor behavior.
How?
So, you know, that
Where's your dome?
it doesn't matter what we have, because when you present poor arguments along with poor attitude and behavior, people on your side, they emotionally don't want to agree with you, and so then they look into flat Earth and they become flat earthers. So thank you.
Yeah, I mean, I would be
I'll have to show Robert.
Two versus two with somebody.
I'll have to show people how Robert behaved.
Yeah, you're asking for a citation. You're asking for a citation that helium gas goes to the bottom of containers, right?
Dude, you still haven't brought it up?
In a vacuum chamber?
Yeah, that's what you guys are asking is for helium. Like humans are made of helium,
Yeah.
rocks are made of helium, and trees are made of helium, right?
Robin, you already agreed with me. You
Humans
would
are
need
made
like
of
a
helium?
mile-high, tall vacuum chamber.
Where are you getting
Remember you
that?
agreed?
No. The reason why I'm saying that, Taylor, is because you're only focused on one element on Earth. So we are
Humans are not made of helium.
we are not exactly. That's the point I'm trying to make to you.
Dude, what do you have right now?
Humans are made of helium.
We are 70% water. We have calcium, iron, and you know.
Dude,
all
stop.
this-
Why is this guy allowed to speak?
So what I'm saying to you is that we are going to the ground definitively. But you want to see a demonstration of helium?
Yeah, sure.
Dude, the amount of helium in the human body is essentially zero.
You know, it is. I know. I'm just saying. I am.
Dude.
Okay. Hold on. Wait.
Wait, let him talk.
Oh my.
It's such a dumb conversation, bro.
Right. What I'm saying to you, Taylor, is that we are not made of helium. Rocks are not made of helium. Leaves are not made of helium, right?
Just contradict yourself.
Why are you focused on one element that and gas has an intrinsic property
Dude, has it been demonstrated?
Bro, more than there's way better globers we could be debating right now. Why do we?
Robert, has it been demonstrated?
I was literally
Yeah, Morgan, can you
throwing
take over?
Rob with flat Earth earlier.
Robert, has it been demonstrated?
Do you think he's
Yes or
from
no?
his position?
Yes, Rob is terrible. He's like probably the worst glober on here.
What has been demonstrated? What has been demonstrated?
Dude, you already know what we're asking for. Has it been demonstrated? Yes or no?
What? That helium.
Oh my, you are so dishonest, dude.
And hydrogen and helium falls to the bottom of the gas
But
chamber.
Taylor, you're going to remain a flat earther because we cannot demonstrate that helium goes to the bottom of a container.
Okay, so that's contention because the thermal motion, right? The thermal motion will cause it to continue, Robert. I'm responding to what Rob is saying. Why am I being interrupted so much? Yeah, the thermal motion is going to be stronger than the force of gravity. It's never going to settle at the bottom of the container. That's why you need a mile-tall container. You conceded to that earlier. So why are you still pretending like you demonstrated helium gas is going to coalesce at the bottom of a container and make a pressure gradient? Like, why would you say that when you didn't demonstrate it?
Because he's dishonest. Simple as that.
Because of this one is about what? Do you know what he just said? What did he just say? What did he just say?
Everybody knows what I'm saying, dude. We're on this conversation the whole time, dude.
Yeah, I'm just saying. He doesn't know what you just said, but he's like, oh, because he's dishonest. What are you talking about?
Whatever.
Everybody gets it, man.
The point is, you need a very tall container. You get a very tall container to demonstrate this helium experiment. You
haven't done it.
Probably,
So in other words, you haven't demonstrated it, dude.
Okay.
Robert need more people on his
No
side.
problem. Okay, no problem. So check this out. No problem. Like
Yeah,
I said
that's
to you-
what we wanted to know the whole time, dude.
Like I've said this to you 100 times, right? The Earth has more things than helium. You're focused on helium, and helium is going to keep you a flat earther.
Yes,
You
that's
just said
fine.
that you had proof. I'm just asking for your proof. That's all.
No.
Yeah.
Helium is going to keep you a flat earther. Helium, that's it.
That's
You're just
fine.
asking me to prove your
That's
claim.
not
See,
the only thing.
helium is going to keep you a flat earther, Taylor. Think about
Okay, Robert, can you just stop repeating yourself? Thank you.
so
Honestly,
wait,
it's fine.
wait, guys,
like normal.
Listen,
Oh, guys,
listen,
look. This is the
listen,
thing.
listen,
Everything ever
let me-
pointed to the
let me
fact
say
that.
this.
Hold on, Rob. Please stop. Andrew was speaking. Just let Andrew speak, and then if you want, you can respond. Thank you. Go ahead, Andrew.
Yeah, so what Robert is saying is that everything, we believe this, by the way, everything on the Earth, everything everywhere points to the idea that the Earth is a globe, but we saw that helium does not sink to the bottom of a vacuum chamber, so we're just going to reject the globe, even though we all know it's a globe, but because of helium, we're rejecting it. That's his straw man.
It's so funny. It's like another word salad, except he's a glober.
Okay, he has in his eye. Profile, he's like, this is a proof the Earth is a globe.
That's what I'm saying, brother. Let's
Sorry, container.
And Robert, we're going to unmute you, but the problem is what you were sharing earlier.
Dude, why do we get? Let's not unmute him.
Okay, maybe we don't have to, but or maybe we can change topics, or maybe another glober wants to step in, and then we can unmute. But Robert, what you were sharing earlier was just an observation, right, about the gradual or the gradient, the pressure gradient, that didn't really solve or prove what we were trying to look for.
No, that's a demonstration that you need. Nowhere in the scientific method do you require four walls. Nowhere in the scientific method that you require four walls. You have to listen to this. You can take your experiment into your environment. The fact that you have pressure gradients in your environment is your demonstration that low pressure can exist next to high pressure without a wall, without any surface, without any hard surface. That's your demonstration.
Okay, Robert,
let me finish what I'm saying here. It's important that you guys understand it. Right? The ideal gas law does not specify a container.
You can have a volume then.
The volume is the volume of gas. That's what the V is. And I'm telling you right now, if you pressurize gas, the volume, if you pressurize gas, even in a container, the volume of the gas reduces. So why does the
You put
volume
evidence for your claims, and then you need to stop talking. You've been talking a whole lot. I don't see any evidence. You said earlier that helium will fall in a vacuum chamber, that it will fall, and you have not posted any proof to that, even though multiple people have asked you to. So please just go get that evidence and let someone else talk.
Taylor, are you made of helium?
Oh, no, I am not.
So why are you putting your stake in the ground by a specific
I haven't done that. I'm just asking you to prove your claim.
Robert, did you say that helium would fall to the ground earlier? Did you say that it would fall to the ground?
Yes, they did.
That's
Prove it. Oh.
Wait, Robert, chill. So, did you say that helium would fall to the ground, yes or no, earlier?
Yes, helium will go to
So,
the bottom of the
substantiate it. You may not do anything else until you substantiate it. Thank you.
Okay. Until he gets his evidence, we're going to mute him so he can go find it. Until then, somebody else can talk.
Okay, thank you, Taylor. Yeah, I was hoping to ask Rob. So, Rob, if you're listening, can you please provide another?
You're gonna ask
No.
What are you doing? Are you crazy?
Hold on, he's going to remain on mute, like Taylor said, but I wanted to make, if he's listening, I was just asking him.
Dude.
Okay, never mind. I'll just send him a private message in the text. Go ahead, guys.
Okay, so here's the thing. Rob is technically correct. The helium does go to the bottom of the container, but it also goes
Oh my
to the top
God, dude.
and
We're
the sides.
doing it again. We're doing a global reset. It's great.
Dude, it's in equilibrium, dude.
You didn't listen. You crashed out. It was a joke, and you didn't even listen, and you missed it. So that's on you.
Well,
Yeah,
you're admitting you're trolling?
That wasn't me.
It's a joke.
That was
A joke isn't trolling. Calm down.
No, he got the last part. You didn't catch the last part. Was it? What I was saying is, why does he say that you can have a high pressure next to a low pressure system in your environment? Like, what does he mean? Like, you can have like high psi next to low psi?
It's just circular reasoning. He's pointing to the gradient of
Nobody
pressure.
knows.
I know we have gradients, but they're not right next to each other. Like you have to go like quite a ways before you'd have to consider this is low and this is high. They're not right next to each other. That's just stupid. Unless you consider low and high one whatever.
Gradient. Yeah.
What's the largest gradient? What's the largest gradient that can exist next to another? Right. Not another gradient, but what's the largest span of a gradient that could exist for a gas?
Right next to each other. I don't know. I'd like to know the answer to that. But I know one thing: you ain't gonna have like this big open space next to even 0.00000 pressure or 0.1 of pressure, because that pressure will freaking go to the available space, and it'll be like it's not. Dude, the idea of space next to a pressurized system is just absurd. And
I mean, like the lower pressure. I know. If you go to sea level, there's one pressure, and you can go 10 feet up, and there's a lower pressure. Like, do we observe this? This is how your phone altimeter work.
Okay. I have a question regarding that.
I'll say that's not high pressure and low pressure. When he says you have high pressure existing next to low pressure, I
agree. Like if you have like a air compressor and you let the air out, it comes out. You have to have a container to do that for sure.
Yeah, well, I'm talking about like in our environment, like maybe even in like a crazy weather system, you might have I don't know. Maybe you would have a high pressure next to a low pressure in some kind of hurricane. So who freaking knows? I don't know. I'm not a weatherman, but.
Thank you, Bear. I have a question for Pink.
Thank you, Bear. He's so freaking. Oh gosh, you're so polite. Thank you so much for your answer, Bear. That was really helpful, and that was actually pretty stupid. I'm sorry. You're very nice, though. Thank you.
Oh, thank you. I had a question here for Pink since he's engaging from the globe side. Pink, can you please demonstrate or show the room here gas pressure without a container that does not include Earth? Thank you.
No, I can't. But I'm not saying nobody can, but I can't.
Okay, thank you.